So let's get started. So we're going to start at the very beginning. What is earthquake early warning? Earthquake early warning is not prediction. It's basically saying that the earthquake has happened and that you're about to feel shaking. For the sake of completeness, because I don't know what everybody knows about various things, we have our earthquake. It starts here at the epicenter. We have our waves that move away. Oh, you can't see the cursor. The waves that move away from the epicenter, which then get triggered at our stations. We then estimate the size and location of the earthquake and provide warning to people that they're going to feel the shaking. Shake Alert is the West Coast Earthquake Early Warning System, and sorry, just to say, we have all these partners down at the bottom. Shake Alert has two seismic algorithms that are used to detect earthquakes. The first of which is EPIC. That's the one being developed here at UC Berkeley. EPIC estimates the earthquake location and magnitude. EPIC is the algorithm formerly known as ELARMS. It is a point source algorithm. It is generally the fastest algorithm with the most accurate location. It is a network-based algorithm requiring triggers from 4 stations to alert, and uses up to only 4 seconds of data at each station to estimate the magnitude and location. To trigger, EPIC uses a short-term average over a long-term average method. It is very sensitive, and so we often trigger at the very start of the P wave, as long as there's no other earthquakes happening right beforehand. In order to create an alert, EPIC uses triggers from 40% of nearby stations, requires that 40% of nearby stations are online in order to create an alert. So for example, for this earthquake here, the actual earthquake epicenter is the yellow circle. The green circle is EPIC's estimated location. We have 4 green triangles, which hopefully you can see there. Those are the ones that have triggered so far. We have a few yellow stations that are surrounding it. Those are the ones that are within the distance, the radius from the estimated epicenter to the furthest triggered station. And then at this time, we had 4 stations that were offline at the time. So using those 4 stations that triggered, it estimates the location, says, okay, at least 40% of the stations nearby are online. Go ahead and create that alert. As mentioned, EPIC estimates the location using those P-wave arrival times and a grid search method. And it estimates the magnitude using observed peak displacement and the station to epicenter distance. Now, once the alert is created, the location and magnitude are updated as more and more stations are triggered. So as each station, as the waves moves out, as they trigger, and then they send their data, and the stations that are closer send more data, we continue to update the magnitude and location estimate. Now, I'm going to primarily talk about EPIC today because we used EPIC in running these simulations, but I'm going to just mention finders for completeness again. Finder is our finite fault rupture detector. It estimates the fault location, the length, and the orientation of that rupture. And it does this using image recognition techniques. Again, I'm not going to go into detail, but just to give you an idea of what our different system parts are. Here's an example of Finder event evolution. You can see with just a few seconds of data, it has its initial location and magnitude estimate from the fault rupture there. And you can see how that increases with time. And you can hopefully see the stars there. The stars, those 3 stars, outline the estimated rupture there. Shake Alert also uses a geodetic algorithm called GFAST. That particular one uses, it gets the earthquake magnitude from the peak displacement. Those 3 algorithms create their individual solutions, which are then brought together by the solution aggregator into a single unified solution. That then, I'm giving you the cliff notes here, that then gets used to estimate the ground motion, again, using the location and magnitude estimate. And the 2 products that Shake Alert produces are a contour maps with the polygons in the upper right. That's the one that's used by most Shake Alert users. We also have a grid map in the bottom right there. And these are the contour maps are the polygons that define the areas of MMI intensity. And again, that's what you're going to get for the WIA alerts, cell phone alerts, et cetera. Those are the ones that use those alert polygons. Okay, so we have these algorithms. We want to know how well they work. So how can we do that? Well, one of the current challenges for earthquake early warning is that we don't have many big earthquakes. Over the last 30 years, there's only been 5 magnitude 7 earthquakes on the west coast, or on or near the west coast. There have been 25 magnitude 6.5 or greater over the last 30 years, which is a little bit better, I guess. I mean, it's quite a few more. We currently have in our Shake Alert West Coast testing dataset this number of earthquakes in the various magnitude ranges. So you can see for those big earthquakes, it's really not that many that we are currently using. And in the biggest earthquake ranges of the magnitude 6 to 7, the earthquakes that we currently have data for are in this table here. And these are organized by magnitude. One thing you might note is that if we organize them instead by date, by the year that the earthquake happened, a lot of these earthquakes are much older. And so that's not as useful for us. And one of the reasons for that is because, as you would expect, our seismic network didn't look the same way back in the day as it currently does. Here's some examples. This is a figure from a 2013 paper showing some of our stations in California. And you can see that there are 377 stations in this map. Here's a more recent figure from Shake Alert from 2018. And at that time, hopefully you can see, but the black dots are the ones that are currently, at the time, 2018, were contributing to Shake Alert. And then they had proposed these new stations as the yellow dots. So you can see there's been a huge change in what our network has looked like from even 2018, but of course, much further back when we were for some of those larger earthquakes. And again, to give you an idea of our station build-out, this is the Shake Alert network and how it has evolved since 2015. It starts just with California because we were initially just looking at events within California. We now create alerts for Oregon and Washington as well. But what you can see is that the network, hopefully if I can play that, you'll see the date progressing in the upper right-hand corner. And hopefully start seeing, there we go, more and more stations that are being added to the network. The final proposed Shake Alert network has, I believe, about 1,700 stations. So again, if we go back to our table of earthquakes in our testing data set, we have 5 earthquakes. But of those 5 earthquakes, the only one that is like remotely close to our current network was the Ridgecrest earthquake of 2019, the magnitude 7.1. And as you may or may not know, it happened out here, which is pretty far out there. It's in some of our sparser station coverage area, and definitely further away from most of the populated areas. So again, it doesn't really tell us how well our system is going to do for a really large earthquake with our current network configuration, especially with regards to alerting population. So how can we improve testing? If you guessed high resolution simulations, you're right. Yes, that's good job. So Dave was kind enough to provide us with these Hayward fault simulations. We have 5 simulations that we ran through EPIC. So again, EPIC is our point source algorithm. As mentioned, we had those 5 epicentral locations on the fault there. And what we did was we used our current network configuration and used the grid point closest to our current network, our current stations, in order to create this simulated network of stations. So instead of using that nice, very regular grid, we were using only those grid points that were next to a station that we currently have in our network. So we've seen these all. These are the 5 simulations, and we ran them through EPIC, and the fantastic thing is it worked really well. So on the right, we have the EPIC magnitude evolution with time, and you can see from the left side of the magnitude on the y-axis there that the magnitude increases from about magnitude 5, and it goes up to about 7.1, which is fantastic, and it's very much the behavior that we would expect from EPIC. On the right, there's the distance error in kilometers, and you can see our distance error is fantastic. And that's, again, not too surprising with the simulated data. It's very clean. We don't expect to trigger in the wrong place. We expect to trigger right at the start of the P wave. So the fact that we locate the earthquake very precisely is great, and it also means it's easier for EPIC to estimate the magnitude of the earthquake if EPIC doesn't locate it well, then it's harder to estimate the magnitude. So you can see that these two go hand in hand to give us a really great solution. That was the first simulation, so we tried another one. We have another one here. This one is slightly different, and the great thing is we did see variation in the results. We didn't just get the exact same curve for each one, which I think is great because it really shows how realistic these simulations are. We would expect to see slightly different solutions from EPIC based on directivity and exactly where the stations are located relative to the epicenter. So you can see this one here gets up to 6.9, so not quite as high, but I would say that's pretty dang good for earthquake early warning. This is the third simulation here, again about 7.1. The fourth one. This one was a little high. This one got up to about 7.4. Again, it's showing some of that spatial variation. If we look at some of the ground maps in the bottom, the center plot there, we can see that we have some stronger ground motions right around the epicenter there, which may contribute to why there's a slightly larger magnitude estimate for this event. And finally, we have the fifth one down in the south. So when we put them all together, we can see that overall, EPIC was able to do a really good job. It was fantastic that the data worked. We ran it through our replay program with no problems, and I think we got some very realistic solutions. Now, we did try to see what would happen if we made the earthquakes a little bit smaller. So one of my questions was, well, if we estimate it as a magnitude 7 every time, then maybe we're just estimating everything as a magnitude 7. Maybe we should actually make sure that we are able to accurately detect the magnitude. So Arben took a stab at creating a source model for this smaller event. We were hoping for about a magnitude 5.5. In order to match the peak acceleration with the GMPEs, he made the fault area smaller to increase the accelerations, but it didn't work very well. So you can see that our magnitude estimate for this particular run was quite high. So again, this was supposed to be a 5.5. We got about a 6.5, still with a very good location error. So we're going to try next, hopefully, a physics-based empirical fault rupture. So we'll see how that works. So our conclusions are that using high-resolution Hayward fault simulation worked really well with EPIC. Our next steps, hopefully refine that magnitude 5.5 simulation. Also run replays of the other shake alert algorithms. So as mentioned at the beginning, the output from shake alert are these polygons and grid map products. And it would be great to be able to run the simulations through both EPIC and Finder to get solutions that we could then put in and get these types of figures, which we can then compare with your plots of estimated ground motion from the simulations. We can then also just play around with it. We can simulate network outages. So if we have large amounts of all these power systems going down, as was mentioned in the previous talk, what's going to happen to our earthquake early warning system? So that's definitely something that we can play around with and see how well earthquake early warning can do. And that's all I have. Thank you.
Any questions for Angie?
Anne-Marie, I think you need a microphone.
Oh, I'd want to go. Okay.
Thanks, Angie. This is really interesting, really important work, and it's fun to see it come here to this workshop as well. So for over the 5 simulations, were you able to say why some were higher and some were lower? Was it spatial variation of where those peak motions are compared to the stations? Can you back out like which stations are triggering and why you're seeing variations there?
That's definitely something that we can do. I haven't had a chance to do it yet.
Okay.
We just did the runs, but we could definitely go through and see, is it something about the station? Is it about the distance? Is it...
Yeah, well, it's great that it all works. That's
Yeah.
really good
We were
first
just
step.
really excited
Yeah.
that it worked.
Thanks.
Uh-huh.
Any other questions? So I have a question. Is your network, you referred to the fact when you showed the stations, you referred to the fact when you were showing all those stations that was sort of the end game. Are all those stations already out and populated, or how far along that curve are you?
We're really close. For California, we're pretty much done with our build out.
Okay,
So in
great.
Oregon and Washington, they're still working on that build
Okay,
out.
so,
But we're-
you know, your conclusions will now be stationary with respect to the sensor locations.
Yes, exactly.
Okay.
Yeah.
Okay, very good. Thank you.
Thank you.
All right, thanks again.